So welcome to the seminar, everybody. So today we have Simona Paoli, who will talk about weakly globular double categories and weak units. Please, Simona.
Okay, thank you very much. So I'm still struggling with this right-hand side of the place where you see all the faces. If it stays just on the right, otherwise I'll pull it down, and okay, if somebody talks, then I will. I don't know. I'm not used to Zoom. All right, so let's get started. Thank you very much for the invitation. So this is a talk about weak higher categories in dimension 2, so not that high. As you know, the first notion of weak two categories, the classical notion of bicategory of Benabou, but people have also come up with different models of higher categories that were really about going in dimension higher than 2, and they were motivated by several different examples and questions in different areas of mathematics. But in particular, when in these models of higher categories you take n equals 2, you find an alternative model to bicategories. And for various models, there have been explicit proofs of suitable equivalence between the classical bicategories and these various models of weak two categories. Now, there is quite a bit of background that I want to tell you before getting to the main point of the talk. The main point of the talk is a direct comparison between two specific models of weak two categories. One is a Siegel type model that I've introduced, and it's called weakly globular double category. So in dimension 2, it was me and Dorette who introduced this, and then I extended this to any n. And then it's the Joachim-Cox model of fair two categories. And I'm not going to say anything in this talk about dimension higher than 2. However, my real motivation is to use this case as a first step to go to higher dimension. But as you're going to see already in the case n equals 2, there is quite a bit of work to do a direct comparison between these two models. And the point is that I believe this direct comparison has the chance of being extended to higher dimension. And what we want to do is to completely forget about bicategories in this framework, okay? So the whole point is to try and connect directly these two models. So there are three pieces of background that I need. One is about the Siegel type models, one is about Joachim-Cox model, and then there is a more technical bit, which is about, again, the Siegel type model. So I am aware that various people in the audience, I was just looking at the names now, various people in the audience know very well at least one of these pieces of background. But now looking at the names, yes, I think it's possible that there are people who don't know all of them. And so I hope it's still useful that I run through this background. And apologies if at some point you get bored, but there will also be a new part later on. So let's start with the Siegel type. Well, in fact, I still want to give first a bit of an overview. So the Siegel type model, there are, in the sense that I'm talking about, there are three of them. So the first one is the Tamsamani model, denoted TA2 for dimension 2. This was one of the first models of higher categories that was introduced by Tamsamani, was student of Carlos Simpson, a very important model because it really showed how you can use techniques of simplicial homotopy theory to do higher category theory. And these other two models are much more recent. So weakly globular double category is a full subcategory of double categories, and that was introduced by Pronk and myself. And then there is a third model, which is a common context for these two, and it's called weakly globular Tamsamani two categories. These three models are all suitably equivalent. And in a paper with Pronk, we also looked specifically at the equivalence of weakly globular double categories with bicategories, which is something of its own interest. But for the purpose of this talk, we forget about this because, as I said, I don't want to use bicategories. And the reason for this is that it's a little bit misleading because remember that every bicategory is biequivalent to a strict two categories. this is what makes dimension 2 a little bit, you have to be careful when you work with dimension 2. And if you are looking at things that you hope to generalize in higher dimension, you have to be really careful not to try and indirectly use this bi-equivalence of bicategories with strict 2 categories. So I'm going to forget about bicategories altogether. Then there is the Koch model, which is called fair 2 categories. And it's, again, it's the case n equals 2, but it has a model of fair n categories. And this encodes the idea of a weak higher category with strictly associative composition, but weak units low. So why was this model developed? He developed it to give a formalization to the weak units conjecture that was formulated by Carlos Simpson, which says that every good model of weakened categories, that means a model that gives you the homotopy hypothesis in the weakened groupoid case, should be suitably equivalent to a model in which you only the weakness is only concentrated in the units. Okay, so that was formulated. I can't remember. It was several years before Joachim's work, and what Joachim did, he found a specific encoding, I mean, a concrete mathematical model to encode this idea of weak units. But to date, the weak units conjecture, so the proof that Koch's model is equivalent to one of the models of weakened categories is still open, except that I think that Joachim and Joyal had a proof of this in dimension 3 for some special cases, maybe the one object case or something like this. So why I have been very interested in Joachim's work since he came up, I think it was in 2006, because in these fair n categories, there are some structures, precisely the structures that encode the weak units, which are homotopically discrete structures. They are not sets, they are some kind of suitable fattening of a set, okay? And that comes from his theory, from his model. Now, and in those, starting exactly when Joachim model came out, I was already working on this idea of weak globularity, which in those days, I was working in a very special context, internal to groups, because the whole story started from Laudet's model. That's where I first encountered the idea of weak globularity. And then I started thinking that there is really something like a new model of higher categories behind it, but it took a long time. So we worked with David on the non-path connected case. And finally, we did the n equals 2 with Dorette, and then I did the case of general n. But the point is, and I had spotted this already in 2006, is that this weak globularity is precisely about having certain structures that are homotopically discrete. And the discretization, the sets equivalent to these structures are precisely the sets of higher cells. So, it's very natural to ask, are these weak globularity, does it have to do with weak units? And more precisely, is it possible to have a direct comparison with this weakly globular n for categories and Koch's model that would lead us to the proof of the weak units conjecture, because cat n weakly globular is a model of weakened categories because it has been proved to be suitably equivalent to the Tamsamani model and satisfy the homotopy hypothesis. So this is my long-term goal, and you start from n equals 2 to see what's happening. And so this is all I'm going to try and explain, how you can directly compare fair 2 categories and weakly globular double categories. And in doing so, I will precisely show you how the weak globularity condition for the Siegel type model is exactly a space of weak units, and how you can directly compare these two models. And I do believe that these techniques have a good chance of leading eventually to the generalization to higher end. The generalization is not something I've done yet, it's not something trivial, but I think there is a good chance. And also the fact itself of connecting weak globularity with weak units, at least in dimension 2, is an interesting thing in its own right. So, as I said, I now want to go through the various bits of the background. So let me now start more slowly with Siegel type models. So we have the notion of Siegel map, which is elementary. It's about having a simplicial object in a category C with, now I see that, just a second. Okay, I have to take a watch to make sure that I'm not running out of time. So the Siegel map is maps that are associated to any simplicial object in a category C with pullbacks. And it's a map from Xn to this, to the limit of the bottom part of this diagram for every k bigger or equal to 2. And why are Siegel maps very useful? Because they can characterize the essential image of the nerve functor from internal categories in C to simplicial object in C. This is built similarly to what you do for the nerve of a small category. So you have this iterated pullback, then the phase operators are built from the composition, the degeneracy or insertion of identity arrows, and so on. And we can show, one can show that a simplicial object in C is in the essential image of the nerve functor, if and only if all the Siegel maps are isomorphic. I think this observation goes back to Grothendieck. It was very important to get started with the Siegel type models of higher categories, because it means to describe a small category, you say it's a simplicial set satisfying the Siegel condition. And then Tarsamani model is essentially a sort of generalization of this that takes into account the weakness of the structure. Now, weakly globular double categories are can be defined as simplicial object in CAT such that, first of all, the Siegel maps are isomorphic. So by the previous line, this first condition means that we have an internal category in CAT, or what we say a double category, okay? Then we have the weak globularity condition that says that X0 is an equivalence relation, or if you prefer, it's a groupoid with no non-trivial loops. So it's a zero type, it's a one-dimensional fattening of a set. And this comes equipped with a map, which I usually denote by gamma, from X0 to the discrete category on the connected components of X0, which I denote X0D. And this is an equivalence of categories. And finally, we have the so-called induced Siegel maps condition. So this map gamma determines an induced map from this iterated pullback to this iterated pullback. And we require that these induced Siegel maps are equivalences of categories. So how to think about this? So first of all, just a small recap, how can we think of a double category? We can think of a double category as having objects, vertical morphism, horizontal morphism, and squares. And then you can horizontally compose squares and horizontally compose arrows, and vertically compose squares in the same way as you vertically compose arrows. And all these compositions are associative and unital. You have one morphism and two morphisms, which I've not written in the slides, but they're there. And you also have the interchange law. Okay, so it's something that you can very easily visualize geometrically. So that's for the double category. Weak globularity means that these vertical things, so the objects and vertical morphisms, form an equivalence relation. So this means that there is at most one non-trivial arrow, non-trivial vertical arrow between two dots. Okay, and what about now this induced Siegel map condition? The induced Siegel map condition, so this map here, you see this functor is always fully faithful. So to say that it's an equivalence of categories is equivalent to say that it is essentially surjective on objects. So what does it mean to take an object here on the right-hand side? An object on the right-hand side is a staircase like this, because you have to take things which don't match in X0, but they match in X0D. So the endpoints here live in the same connected components. And what is an object on the left-hand side? An object on the left-hand side is an actual staircase. Oops, sorry. Sorry, I'm messing up with the, obviously I'm doing something stupid. Okay. An object on the right-hand side is an actual string of composable arrows, okay? So essential subjectivity says, given this staircase, you can find an actual string of arrows, as well as vertically invertible morphes, squares that lift this. Okay, so it's a lifting condition that is a sort of geometric picture of this weak globularity. So we also have a truncation functor that we are going to use from weakly globular double categories to categories, which is built by applying level-wise in your horizontal nerve. So X is a simplicial object in cat. You apply level-wise the isomorphism of object functor from categories to sets. And this gives you the nerve of a category because of this weak globularity condition. So we call this functor P upper 1. And we also have a notion of home category, not surprisingly. So if A and B are in X0D, you take the fiber of this map, which we call XAB. Okay. So why do we need these two things? We need these two things to give a notion of two equivalence. So a map in weakly globular double category is a two equivalence if it is locally an equivalence of home categories, and after truncation, you get an equivalence of categories. And you think about this as a higher dimensional generalization of a functor which is fully faithful, so that's the analog of condition A, and essentially surjective on objects, which is the analog of condition B. So if you're used to Siegel type model or Siegel categories and these sort of things, this is a very familiar idea. You have a kind of local condition and then a condition up to homotopy. Okay, so now I want to tell you something about the Joachim-Cox model of fair two categories. This is a very nice model that basically takes some of the, oh, sorry. I really, this should not happen. I actually told people that I was giving a talk. I really apologize. I hope it won't happen again. What we want to do is to have a model which is similar in spirit to the Siegel type model, but a key idea is to replace the delta with a different category that encodes the weak units. So that's the fat delta. To go to the fat delta, we want to work with colored categories. So categories in which you have a subcategory containing all objects, and this subcategory is the arrows in this subcategory are called colored arrows. And you have color preserving functors. You can also have a notion of a free colored category on a colored graph, a graph where some of the arrows are colored. So you take the free category on the whole graph, and then W is the free category on the colored part of the graph. So the point is that now, remember that a ordinal can be seen as a category on a linearly ordered graph. So you immediately have a colored version of ordinals. So a colored ordinal is a free colored category on a linearly ordered colored graph. And we can represent this graphically like this. So you have the dots like for usual ordinals, but then you have links for the colored arrows, okay? And you don't put any other arrows here. You also have a functor from this category of finite not empty colored ordinal to delta that contracts all the links. So this is the first idea that we need. And then the second idea is the idea of semi-category, which starts from the idea of semi-simplicial sets. So this is a simplicial set without degeneracies, okay? So it's a functor from delta mono up into set. And if you impose the Siegel condition, that gives you a semi-category. And then you have a corresponding colored notion. So this is what Joachim uses to give the definition of the fat delta. The fat delta is the category of all finite, not empty colored semi-ordinals, which can be naturally identified with T mono, okay? And this projection functor from T to delta gives you immediately a projection from the fat delta, which is T mono, to delta mono, which is included in delta. And this, I will make use of this projection functor quite a bit. So this fat delta basically plays a very similar role in a Koch model than the delta plays in the Tamsamani model. So a there are also a couple of things I want to mention. So there are two ways to include delta mono in delta. There is a horizontal inclusion, where you interpret a semi-ordinal as colored semi-ordinal with nothing colored, or with everything colored. And those gives you these two different inclusions. And these are important in the definition of fair and categories. So what is a fair to category? So we say that it's a color preserving phantom from delta up to cat, where the coloring in cat means just the colored arrows are the equivalences of categories. This is required to preserve discrete objects and pullbacks over discrete objects. Okay, so let's see, let's try to unpack a little bit this definition. So first of all, we have this colored ordinal, the dot, the two dots, and the link. And these give you respectively the objects of objects, the objects of arrows, and the objects of weak units, okay, or weak identity arrows. And then, for example, what does it say to preserve pullbacks over discrete objects? It means, for example, that you take this pullback here, you get, so this push out, sorry, you have a pullback diagram like this. And in particular, what this means is that the restriction to either copy of delta mono op in delta op is a diagram that satisfies the Siegel condition. What this means is that this category of arrows and this category of weak arrows carry a structure of semi-category internal to cat, okay? Another thing that is proved by Koch is that these two maps from U to O coincide. And in fact, and this is not all, what you can show is, and this is a sort of useful practical criteria, whether you have a structure that is a fair to category. To give a fair to category is enough to give a discrete category of objects, a category of arrows, a category of weak units, together with a commuting diagram like this. And together with semi-category structures on this and this, so I've not written the composition here, but it's there, and it's assumed to be associative, so you have a semi-category, and then you have a semi-functor like this. And basically A and B are enough to reconstruct everything else because of the Siegel condition. And finally, what does color preservation mean? Sorry, I mean, I really apologize. I'm really angry about, I think it's the shift in time between here and Italy that makes my parents absolutely confused. Apologies about this. So the color preservation tells you that these composition maps, which are, as well as these two maps, so these 5 maps are precisely the images of these maps here. I just want to do something. If you give me just a second, that I'm going to log out of Skype because I'm really worried. Can you bear with me for a second, because I'm really a bit worried about if I manage to log out of Skype. How do you log out of Skype? Oh. I really apologize about this. Okay, sign out. Okay, this should prevent my family from calling me. I hope there are no emergencies or something. I'll find out later. Okay, I'm still on sharing, right? Am I still sharing?
No, now we lost the slides.
Okay, I'm going to get back there. Okay. All right, and now I have to, I guess, all right.
Yeah, it's perfect.
Okay, all right, so what is color preservation? So you look at these maps, these 5 maps, which are the images of these maps in the FET delta. And you can show that these 5 maps generate all the vertical arrows. And so the color preservation is equivalent to say that these 5 maps are equivalencies of categories, okay? So we have a pretty small set of things to check that a given structure is a fair to categories. And I'm going to use this criterion in a moment in building fair two categories from weakly globular double categories. All right, so this is the second piece of background. And now another thing is that you can build a truncation functor from fair two categories to categories precisely in the same way that we did for the Siegel type model. You apply level-wise the isomorphism classes of objects functor. This also gives you a home category and the notion of two equivalents in fair two categories in a way completely analogous to the Siegel type models. So now what about this third part of background? We need this, and it's again about the Siegel type model. So what is this third model, the weakly globular Tamsamani two categories? The definition is the same as Cat2 weakly globular, except that you don't require that the Siegel maps are isomorphism. So you have a simplicial object in Cat. X0 is an equivalence relation. The induced Siegel maps are equivalences of categories. Okay, and so if X0 happens to be discrete, then you have a Tamsamani two category. So you see that this Tat2 weakly globular encodes Tat2, and if you have the Siegel maps, you have Cat2 weakly globular. So it's a generalization of both these models. So the reason I use this in my book is it's a common context in which to do comparison between the Tamsamani model and the weakly globular N4 categories. But what I want to tell you now is how to build a pseudo functor out of this thing. And this is requires a slightly new notion. So we are looking at a certain class of pseudo functors from delta up to cat, those for which, first of all, you can say that H0 is discrete, because in this case, you can say that this diagram always commutes. If this was just any pseudo functor, this would only pseudo commutes. But if H0 is discrete, then it commutes. And so there is a unique Siegel map from HK to this limit of the bottom part of this diagram. And so we define Siegelic pseudofunctor to be the full subcategory of pseudofunctors from delta up to cat, whose objects H are such that H0 is discrete and all the Siegel maps are isomorphism. Okay, so why is this an interesting thing? Because you can show that there is a natural way to construct a functor from Tat2 weakly globular to Siegelic pseudofunctor by taking these entries. And then how do you build the structure maps for the pseudofunctor? Well, from the induced Siegel map condition. And there is there are various ways to prove this is a pseudofunctor. You can just do all the calculation, but that's very boring. Or you can use a standard technique of transport of structure along an adjunction to show that this is a pseudofunctor. So that's why I call this functor TR, which stands for transport of structure, TR2 in dimension 2. Okay, so now this is something you can build very easily, but now the crucial point is that, as you know, we have a strictification of pseudofunctors into strict functors that can be built in lots of different ways. In particular, I'm using the particular expression of strictification that was in a paper of John Power and also was refined by Steve Luck. That is a very, very explicit strictification functor. And using this one, you can show that this strictification functor, when you calculate it on a Siegelic pseudofunctor, gives you back precisely a weakly globular double categories. So weakly globular double categories emerge as strictification of Siegelic pseudofunctors. And well, there is also a higher dimensional generalization of this, but this is non-trivial. It's what it's in my book, and it's not important for this talk. But what I want to stress is these pseudofunctors are quite important for this theory. And the strictification is something, it's a very classical piece of literature, and it immediately makes this weak globularity condition appear in this more rigid structure. So Cat2 weakly globular is a full subcategory of double categories. All right, so I think I'm done with the background. I'm really getting worried about the time. How much time do I have left?
You have half an hour and
yeah. Okay, that sounds good. Half an hour sounds good because I'm more or less halfway through. All right, so now this is an overview of the new part, so the non-background part. So the central result is this orange box. So we have a pair of functors between the two models that induce equivalence of category as after localization with respect to the two equivalences. And to get here, we need 3 inputs. So first is the construction of the functor F2 from weakly globular double categories to fair two categories. And this also comes equipped with a more explicit map to compare F to X with a suitable modification of X, which I will explain what it is. And so this functor F2 necessitates a slightly new notion, which is what I call strong Sigalic pseudofunctors. Then there is the blue input, which is the functor on the other way around, from fair two categories to weakly globular double categories. And this is something quite technical that requires various properties of the fat delta. So when you have these two functors, then the proof of the equivalence after localization means that you have to prove that certain zigzag of maps are true equivalences. And this is the part where I need something new, namely a new context that gives me a way to build this zigzag. And it's what I call the category of weakly globular fair two categories. That comes with the result which is similar to the one that you have for the Siegel type model, but involves the fat delta rather than the delta. And we also have a way to go from weakly globular fair two categories to fair two categories. So I will come to this yellow part at the end. This yellow part in itself is quite technical, but as I said, it's something needed to actually have the proof that you get an equivalence of categories here after localization. So what I want to do next first is to give you some ideas about the construction of the functors F2 and R2, so the green and the blue box, and then I will come to the yellow box at the end. So what about the functor F2? So the functor F2 is actually a very simple idea which occurred to me relatively recently. So, and when I found this, I felt a little bit silly that I had not noticed this before, but over the years, I've been very interested in pushing this to higher dimension and prove that we have a new model of weakly globular M4 categories, and I had a little bit forgotten about the case n equals 2. And when I revisited it, I realized there is a very simple observation that naturally leads to a functor from weakly globular double categories to fair two categories. So for this, I want to give you first this notion of strong Sigalic pseudofunctor. I mean, this is just a name. I don't even know whether it's the best name. Maybe some of you can suggest a better name. So we have an inclusion functor of delta mono op into delta op that induces a functor from pseudofunctors from delta op cat to pseudofunctors from delta mono op into cat. So a strong Sigalic pseudofunctor is a pseudofunctor such that this restriction is in actual functors from delta mono op into cat. Okay, so that means that you have a functor from strong Sigalic pseudofunctor into delta mono op into cat. Okay, the restriction to delta mono is just a functor, and a morphism of strong Sigalic pseudofunctor is a pseudo-natural transformation such that this is a natural transformation in here, a strict natural transformation. Okay, given this definition, so here is the crucial point. It's the observation that, so we had this transport structure functor from tattoo weakly globular to Sigalic pseudofunctor that I told you earlier. It's just built in a natural way. Remember that this tattoo weakly globular is a model that encodes both the Thompson-Mani model and the weakly globular double category. So the observation is that when you restrict this functor to weakly globular double category, the essential image is a strong Sigalic pseudofunctor. Okay, and this is not true for tattoo weakly globular, and it's not true for tattoo, but it is true for cat2 weakly globular. So how do you see this? So what does it mean to show? So if X is a weakly globular double category, we need to show that this is a functor from delta mono up into cut. And it also satisfies the Siegel condition. So how do we show this? A functor from delta mono up into cut is a semi-simplicial object. So what we need to show is that we have the semi-simplicial identities, which are these ones here. And this is actually a very easy thing to prove because the induced Siegel maps for weakly globular double categories are actually injective on objects. So if you take a pseudo inverse, you have that mu k, so nu k, mu k hat is equal to the identity. And so you see that, so this is the part that I actually didn't tell you precisely, but I said in words, how do you build the structure maps in this T2, TR2X in the pseudo functors? You build it using precisely these equivalencies of categories from the induced Siegel maps. So when you do this, you see that this condition determines a cancellation that precisely means that the semi-simplicial identities are satisfied. Okay, so it's precisely the induced Siegel map condition on weakly globular double categories, the fact that this is injective on object, that means that your structure is when is you restrict it to delta mono up is actually a functor. Okay, and this is what gives you the semi-category structure on arrows that is needed to build a fair to category corresponding to a weakly globular double category. So we build a functor F2 from weakly globular double category to fair to categories. And how do we do this? So the object of objects is the discretization. The object of arrows is x1, and the object of x of weak units is exactly x0. Okay, and remember when I presented the Koch model, I said we have this just three conditions to check that something is fair to category. So we want to have a diagram like this, and this is what you get. Remember that sigma 0 delta 1 is the identity, so this diagram commutes. And then we have the semi-category structure. So here is the point of this previous observation. The semi-category structure on x1 and x0 comes from the fact that this is a strict functor from delta mono up into cut. And by definition, you immediately have the Siegel condition. So that what gives you all the associativities that you need in a fair to category. And then what was the third condition? The third condition said that this map gamma from x0 to x0d, as well as these three maps are all equivalencies of categories. And this is trivial to check from the definition of weakly globular double category. Okay, so all this is quite, quite elementary. The only thing that is really the content of this is that because of the induced Siegel map condition in the weakly globular double category, when you restrict to delta mono, you have a semi-category structure, and that's what is needed in Koch model. So that's the construction of this functor. You can also easily check that the truncations are of x and the truncation of f to x are the same, or well, isomorphic if you like, and that xab is isomorphic to f to xab. And so in particular, this immediately implies that this functor f2 preserves two equivalences. Okay, I think in the end I didn't insert this thing here that I was telling you in the overview. There is a way to compare f to x to a suitable modification of x. So this is this pi star tilde x is an object of fat delta up into cat, and it's a natural way to somehow to view cat2 weakly globular inside functors from fat delta up into cat. I don't want to go into too many technical details here, but there is a natural way to do it. And so this will be one of the ingredients. So there is a map like this, which will level-wise equivalence of categories. And this is one of the things that then are needed when in the orange box, we need to prove this zigzag to see the equivalence after localization. But I don't want to go into too many technical details. Okay, so this is for the functor F2, the idea of how you build it. Now I want to give you some idea on the blue box, so how to build a functor the other way, from fair to categories to weakly globular double categories. So again, it's a fairly technical construction. So this part is more technical than the functor F2. And so these are basically how you build it. First of all, you have to dig a little bit more deeper into fair to categories and the fat delta. So you can show that we have, for each K in the fat delta, you have equivalencies of categories like this. And if the main point about this is that if you have two maps in the fat delta that correspond to the same mapping delta after application of the functor pi, then you have this behavior that this compositor is equal to this composite. Okay, so this takes quite a bit of work to prove, and some properties of the fat delta that I don't know, maybe Joachim knew about this, but I didn't know, so I had to work them out. And then you define your functor t to x n to be exactly xn, but how do you define it on maps? So if you have a map in delta op, you choose a map in the fat delta op that goes to f under the functor pi, and you define t to f to be given by this composite. Of course, this only makes sense because we have proved this fact here. Okay, so each of these is a kind of proposition lemma. It's quite a technical thing. If you show this, then this is well defined, and then you define the two-dimensional structure, and you show that this is a pseudo functor from delta up into cat. The sigalic part is, and the strong sigalic part again, are immediate from the construction. The main thing is to really give the definition of the pseudo functor on objects, on maps, and the two-dimensional structure. And then everything else is quite straightforward. But this is not trivial, okay? This part, at least I have not found a simpler way to do it, and it requires some digging into the category of fair to. And so what do you do with this? Well, we know that we can strictify sigalic pseudofunctor into cat2 weakly globular. So in particular, we can apply this functor to strong sigalic pseudofunctor. And so this gives us a functor, composite functor, which I denote by R2 from fair to categories to weakly globular double categories. So this is, this is now, oops, I want to go back. Okay, so I've covered now the blue box. As I said, it's a bit of a mystery here. What I'm saying is that there are various properties of the fat delta that are required for the construction of this functor T2. Okay, so now let me give you at least a statement of the orange box. So it's the comparison result. The comparison result is that these two functors induce an equivalence of categories after localization with respect to the two equivalences. So what do we need to do to prove this? We need to say if you start from x in cat2 weakly globular, we are going to produce a two equivalence between x and R2 F2x. And given a y in fair to categories, we produce a zigzag of two equivalences in fair to between y and F2 R2y. Okay. So if we have this, then it means that after we localize with respect to the two equivalences, we find an equivalence of categories. The first bullet point requires, well, what the construction of the two functor, as well as this this comparison map between F to X and that modification of X and a little bit of work, but it doesn't require anything substantially new. But the second bullet, it appears to be a bit more difficult. And basically, I have tackled it by introducing a new context, which I called weakly globular fair to categories, because the zigzag that I managed to write initially lives in this bigger context, and then I do something to it and I transform it into a zigzag in fair to categories. I am not claiming that this is necessarily the best way to do it. Maybe there is a simpler way. I have not found it. But I would say that from my experience in working with the Siegel type models, it's not unusual that you need a slightly bigger category in which to do comparisons. And that's one of the cases here. And you will see that this new player, the category of weakly globular fair to categories is, again, it's an entirely natural generalization of fair to categories. So maybe I should have started the whole thing from fair to weakly globular. I don't know. I mean, I am just presenting one way in which I managed to do these proofs. Okay, so basically this is now the yellow box, which, as I said, I would tell you about at the end. I just want to say a few things about it. I actually think it's fairly interesting because this result, this strictification result, is something that follows very closely what happens in the case of the weakly globular double categories. And here you have the usual delta rather than the fat delta. So it's a result that exploits some similarities between the fat delta and the ordinary delta. So to give you a few ideas about this, so first of all, I want some notation about the fat delta. I'm considering here, so this, I don't even know how you call this in English anyway, this strange one. It can be either the one of delta mono, or it can be this colored ordinal, which I also denote 0, 1. It's just the one link. And then I have the maps delta 0, delta 1 are the usual one if you're working in delta mono, but they are these maps if one denotes the link. Okay, so any colored ordinal is a suitable diagram of this form, and you can make it more precise, but that's what you have, and it's essentially already in Koch paper. But so why do I want to use this notation? Because I want to have a notional Sigalic pseudofunctor now from the fat delta up into cat. Now, to have this, first of all, we ask that H0 is discrete, so we can have this commuting diagram, because otherwise it would only pseudo commute. And then we have Siegel maps like this. And so what is this S? This is where you have to be a bit careful with things. So if you have K in fat delta, which has T links of length N1 plus Nk, and then you count, and this S is exactly K. So K is the pi of underline K plus N1 plus Nt. And you can write down everything. You can see it very explicitly. So the Siegel maps are like this with this S iterated pullback. And now the notion of Sigalic pseudofunctor from the fat delta up to cat is, again, very similar. So you ask discreteness, you ask isomorphism of the Siegel maps, but then you need to ask a little bit more. You want these maps, which are images of these maps in delta. This map, you want them to be equivalencies of categories. So it's the modification that you have to put because you are working with the fat delta rather than the ordinary delta. Okay, so we have this notion, and now the new player, and then we're going to connect the two, is weakly globular fair to categories. This is an entirely natural definition. So again, we have functors from the fat delta up to cat, but now X0 is no longer discrete, it's homotopically discrete. You have isomorphism of the Siegel maps, but then because H0 is homotopically discrete, you also have induced Siegel maps, and you ask that these induced Siegel maps are equivalencies of categories. And finally, you ask, as usual, the preservation of colors. Okay. So we have these two notions. And okay, so to just somewhat quickly, you have a notion of truncation functor for weakly globular Fair2 categories, completely analogous to the one for the Siegel type models. So this is the truncation functor P upper 1F. You have a notion of home category, analogous to what you do for weakly globular double category. You take the fiber of this map when you go down with gamma to X0D. And then you have a notion of two equivalents in weakly globular Fair2 categories. It's the whole, I mean, all these are completely expected definitions by analogy with both Fair2 and Cat2 weakly globular. So the main result is that we can now connect these two things, Sigalic pseudofunctor from fat delta up into Cat to weakly globular Fair2 categories via the strictification functor. And it's quite nice to see that the proof of this result is formally analogous to the one of that we had in the original paper with Prong, that Sigalic pseudofunctor from delta up to Cat strictified to weakly globular double category. So again, maybe one should really do everything in this bigger context of weakly globular Fair2 categories from the start. Okay, so now we have this result. We just are going to use it at some point to build this zigzag of two equivalences. So let me explain this next. Okay, so there is just another thing. So we have this functor, and we also have a very easy functor from weakly globular Fair2 categories to Fair2 categories. You construct it this way. You discretize at level 0. You do the sort of completely obvious thing, and you can show that this functor preserves two equivalences. So we're going to use this because we're going to produce a zigzag of two equivalences in Fair2 weakly globular, and by applying D, we will convert this into a zigzag of two equivalences in Fair2, and then we will be done. Okay, so now we are back to the orange, and now the last bit is using this new player, this new context, and this result in the yellow box. I'm going to show you at least the idea of how to build this zigzag of two equivalences that give us the equivalence of localization after equivalence of categories after localization. Okay, so these are the two equivalences that we want to show. Now, again, for simplicity, I have recalled the functor R2. So this is from Koch model to the double model, and F2 the other way around. So one part, so you start from a weakly globular double category. And so this first part is the one where you have to do some work. Okay, so you show that there is a pseudo-natural transformation from T2 F to X to X. And I'm not going to give details here, it's quite technical, but it basically is just a matter of seeing how you have constructed this functor T2, which I told you was one of the most technical bits. But once you have it, you follow through and you have this pseudo-natural transformation. At this point, everything else is formal, okay? So you have the adjunction between the inclusion of strict functor into pseudo functors, and with the left adjoint being the strictification. So by adjunction, you get a corresponding map from the strictification T2 of this, but this is by definition R2. So you have a corresponding map from R2F to X to X, okay? And again, it's completely formal to see that this is a level-wise equivalence of categories. A level-wise equivalence is in particular a two equivalence in Fair2. And so we are done, okay? That means that X is isomorphic to R2F to X in this localization. So this part, as I said, it requires some technicalities, which are really the same level of difficulty as building the functor T2. For the rest is formal, following from the adjunction, between inclusion and strictification, and so you get this part of the equivalence. The second bit is the one that requires the new player. So if you have a fair to category, again, you have first this pseudo-natural transformation, which again, it's technical because R2 require this functor T2, which is a little bit messy, but it's something you can write down. And then you proceed formally. So you just hit this with the adjunction. This gives you a map from strictification of F2 R2 Y into Y. So you have this map here. So this map here from strictification of this into this. And then you also have a map from here to here. This is a general fact about the strictification factor. Okay, so you have this zigzag. Now, you know that Y gives in fair to categories, and you know that F2 R2 Y lives in fair to categories because that's how the functor F2 goes into fair to categories. But then you have this thing in the middle, yeah? And you have to ask yourself, where does this live? So this is where the point where I had to understand a bigger context, because this thing here does not live in fair to categories. There's no way. So I had to understand, where does this live and how can we transform this zigzag into a zigzag in fair to categories? So here the point is that this F2 stratification T2Y is in fair to categories. And so when you, in particular, it is a Sigalic pseudofunctor from fat delta up into cat. And so when you hit this with the stratification, you get a weakly globular fair to category. Okay, so we can say that this is a zigzag of two equivalences in this bigger context. And now we hit this with the functor D. The functor D is a functor that preserves two equivalences. And so now this gives us a two equivalence. This functor D also acts as identity on fair to category. So in here, we just stay with Y and with F2 R2Y, but in the middle now we have a fair to category. Okay, so this is what you do. I don't know if there is maybe a way to do this more simply. I have not found it. As I said, my experience with the Siegel type model is that when you do these comparison with zigzags, very often you need a bigger context. We had this also in our paper with David, which was a more kind of homotopical paper. But it's quite lucky that in the end, we managed to reconduce ourselves to a zigzag in fair to categories. And so that gives you the proof of the main result, which is the orange box. Okay, I think I'm not doing badly with time. So I just want to quickly summarize the main point. So the main point of the talk is a direct comparison between two particular models of weak to category. One is a Siegel type model called weakly globular double categories, and one is a Koch model of fair to categories that encodes the idea of weak units. This direct comparison shed new light on weakly globular double categories because it tells you precisely that this weak globularity condition is about the space of weak units. And the other thing is that I am quite convinced that these techniques are sufficiently general and sufficiently far away from bicategories and from the strictification of bicategories into strict categories, which is something we don't want to have around, right? Because we know that that does not generalize in dimension hydro 2. But I believe this technique have a good chance of generalizing. This comes from my experience with the Siegel type models. These Sigalic pseudofunctors play an important role in the Siegel type models. I also think this generalization is non-trivial. Otherwise, it's not something you just write down and do it. But I really have a good hope that it's possible. I keep been fascinated by Joachim's model. I think his intuition about the weak units and how to encode them was fantastic. And I really hope one day that we'll have the close connection between weakly globular double categories and fair N categories. Now, because weakly globular double categories are equivalent to Tamsamani N categories, that would finally give you a proof of the weak units conjecture. And that would be nice because, as we know, one of the obstacles in working with higher categories is their complexity. So to have a proof that a Joachim model is really a model of weakened categories, I think would have a lot of nice consequences in places where higher categories are used, which, as you know, by now it's lots of places, multiple-type theory, in mathematical physics, and so on. So I really hope that we will get there. Okay, so there is a preprint on this paper, which will be, I will post a new version of it with some corrected typos soon. I was hoping to do it before today, but I haven't managed. So I would, if you're interested in looking at the paper, wait until I get version 2 posted, which should happen in a couple of weeks. I would also be very interested if you want to send me any comments. You can send it to my email address, and I probably would prefer if you stick to my non-academic email. And I think that's all for me, and thank you very much for your attention.
Okay, thanks a lot, Simona. So I'm happy to see that fair categories are still alive. Are there any questions or comments? Maybe I have a question myself. So when you do globular, you take products of delta, so that you're looking at pre-sheaves on delta up, cross delta up, cross delta up, and so on. Yeah. Or just delta. Do you do anything similar with the fat delta?
Well, so not in this talk, because that was dimension 2, right?
Yes.
Probably yes.
Okay.
Yeah. I think this fat delta is really fascinating, and there is more to understand about it. And I think when you start taking products of fat delta, again, there could be really interesting things to do. Yeah.
So fascinating is a kind word. I should say I stopped working with it because it's too difficult.
As you know, I'm a very stubborn person. No, I mean, the thing is, as I said, it really is the homotopically distinct structures that come in your model and in my model, that it's just, I kept thinking, can't just be a coincidence. I mean, they are spaces of weak units, and so I always, also when I look at your work, I'm always surprised at the amazing intuition you had about the fat delta. Maybe you can tell us a bit more about it.
Well, I don't think it's very deep. I mean, simplicial sets have degeneracies, and whether you want it or not, they give you some kind of strict units. So to get rid of them, you have to abandon delta and have units only up to homotopy. And that's what fat delta tries to do. I think it's not very deep. Here's maybe another question. So you did use stratification at several points, or at least one point. So how do you think that will go in higher dimension? I mean, how
yet?
No, but I mean, is it something essential, or is it just for convenience? Or
no, I think it is essential, because so in higher dimension, you have, well, in my book, it is essential in the comparison between Thompsonian categories and weakly globular N4 categories, because you go from Thompsonian categories to, you cannot go directly in dimension higher than 2. From Thompsonian categories to weakly globular N4 categories, you have to introduce an intermediate category from which you can do this transport structure and build pseudo-functors. Yeah, and that's what makes the case n bigger than 2 much harder. Now, to sort of to do this this thing in high dimension, I don't know. I mean, my feeling is that so you see the stratification already happening in dimension 2 when I worked with this weakly globular fair 2 categories, and I think you can expect something similar in high dimension. So it could be that you really need to work with the context. I mean, this is what I'm thinking. You need to work in a bigger context of weakly globular fair N categories, and there are these stratification functors also appear, and as in the case of the ordinary delta, so the analogous, well, you will have something quite analogous for the stratification, I think, but it may not be entirely easy to build from a fair N category in dimension n bigger than 2 a pseudo-functor from suitable from a product of fat delta into cut. So that's the bit which I envisage will take a lot of work, because that's basically what happens in the usual delta case. I mean, I have more and more the feeling that one should really maybe start working from this bigger context and see all these special cases that happens. But the first time you do something, you just try to do it. We will see. But I'm quite convinced that there's a lot of techniques in my work, in my book, that because of these strong analogies between the fat delta and the ordinary delta, a lot of these techniques are going to be useful in this context. And so it's a matter of working through it and see what needs to be done. But I'm really quite hopeful.
Okay, sounds exciting.
I should tell this to the Leicester management.
Yes.
That's the whole problem at the moment. They don't find it exciting at all, as you know. We also have another simplicial God in here, Angie. But they don't find him exciting either.
It's not a question of what we find exciting, Simona, as you perfectly know.
Well, yeah.
Are there any more questions or comments? Then maybe before we thank Simona again, I should look forward to next week. So next week we have Martin Markl from the Czech Academy of Sciences, and he will talk about operatic categories and their operats, May versus Markl.
Wow.
So that's next week at 10 o'clock. And thanks, Simona, again.
Thank you very much. Thanks. I really appreciate it.